Okay, so in today's class, we're going to speak about the trace of Möbius transformations, which is an easy to compute numerical invariant that tells us which type of Möbius transformation we are dealing with by just looking at any of the matrices that represents it. And then we are going to see some of the differences between a PSL2C and a PSL2R. We're going to make a basic comparison between these groups, kind of a rough comparison between them. The trace. So we know that there are 4 types of non-identity Möbius transformations. Namely, if they give us a Möbius transformation different from the identity, we know that it is either parabolic, hyperbolic, elliptic, or loxodromic, right? And to determine the type, something we can do is to first compute the fixed points, and if there's only one, then we know it's parabolic, and if there are exactly 2, then we can compute a Möbius transformation that sends the fixed points to 0 and infinity, conjugate by this Möbius transformation, and find out the scalar alpha such that the conjugation is multiplication by this alpha, right? And then depending on the alpha we obtain, we can decide which type of Möbius transformation we were given. We would like an easier or more straightforward way to decide the type of Möbius transformation that doesn't require us to do all of this. In particular, that doesn't require us to compute the fixed points. So what we are looking for is a function that to each invertible matrix associates a complex number. And we would like, something we would like is that function is invariant under multiplication by non-zero complex numbers, so that it really depends only on the Möbius transformation and doesn't depend essentially on the matrix representing it, right? I mean, so that if you give me the matrix, then with if property 2 is satisfied, then for any other matrix representing the same Möbius transformation, we have the same value of the invariant. That's something we want. And another thing we want is that it's invariant under conjugation, so that if you give me a matrix and then the value of this tau in that matrix or in that Möbius transformation, it is the same as the value of tau on the standard example associated to the Möbius transformation, right? So that a tau of a Möbius transformation is equal to tau of the corresponding standard example. So those are 2 things we want. So that this is that it's really an invariant associated to the Möbius transformations, and that the value at a given transformation coincides with the value of the corresponding standard example. And third, we would like it to separate as much as possible the standard examples, right? So that, for instance, it does not happen something like if I define just tau to be a constant invariant, then of course 1 and 2 are satisfied, but it's not very useful because it doesn't separate the standard examples well enough, right? So we want some separation of the standard examples, Okay, so for instance, we would like tau not to confuse parabolics with elliptics or with hyperbolics, etc. And if possible, for instance, if I have, let's say, two hyperbolic standard examples but with different alphas, that maybe we can hope that tau really distinguishes them. Okay, so that's what we are looking for. Now, look, we already know a function that satisfies one, that is invariant under conjugation here, namely just the trace of matrices. Right? So, namely the trace of, let's say, alpha, beta, gamma, delta equal to alpha plus delta. This function is defined in the invertible matrices and satisfies one. Right? So let's keep that in mind. Now, for any tau satisfying 2, so being invariant under multiplication by non-zero complex numbers, so that if two matrices are scalar multiples of each other, they give me the same value of tau. And that is if two matrices represent the same Möbius transformation, they give me the same value of tau. Then one automatically has a commutative diagram, right? So where if you give me the matrix and you compute tau of the matrix, that value has to be equal to the value of tau at this other matrix, right? Because this other matrix, of course, is obtained from A by multiplying it by a complex number, right? Okay, and also if you give me any matrix, tau of it has to be equal to tau of minus it, right? So what this so if 2 is satisfied, then we know that there must be such a commutative diagram, and what this tells us is that maybe something we can do is in order to define tau for any matrix is kind of just define tau in terms of first performing this operation, and just taking care so that tau of a matrix be obviously equal to tau of minus it, right? So something like taking some square or something. Now, remembering that we already knew such function, we come up with this definition of the Möbius trace of a matrix. So tau, the Möbius trace of a matrix, is, well, as we said, we first divide by the square root of its determinant, any square root of its determinant, and then take the trace, and then in order for the value to be the same at minus the matrix, so at minus here, we take the square of such thing, right? And then in terms of the entries of the matrix, then one easily computes this, and then here you see somehow the fact that here we take the square automatically tells us it doesn't matter which square root of the determinant you decide to take in between. So this is the Möbius trace, and then by construction it satisfies 1 and 2. So it is invariant under conjugation here, and also invariant under multiplication by non-zero complex numbers. This I can leave you as an exercise. It's pretty much a consequence of the considerations I made. Okay. So now we have to investigate about 3, right? What's the behavior of tau on the standard examples? So let's see. So if we have a parabolic standard example, namely a translation, you see already written here, you know, with determinant 1. We see, yeah, I mean, it's just obvious that when we apply this formula, we obtain a 4. And this is for all parabolic, right? So and this should be no surprise that any parabolic gives me the same, because we know that all parabolic Möbius transformations are conjugated in mod plus. Okay, now for the standard examples that have exactly 2 fixed points, and being standard, then this means that the fixed points are 0 and infinity. That is, for those that where it's multiplication by some alpha. Well, if we divide first by the square root of the determinant, we obtain this. Okay, and then we compute, right? I mean, after having divided, we compute, and then we obtain that in terms of the alpha of the multipliers, the Möbius trace is equal to this, right? Alpha plus 2 plus 1 over alpha. Notice that here I'm already writing tau, not of the matrix, but of the Möbius transformation, right? So this I already justified why I can do that. And then I need some basic lemma, like it's an exercise of calculus 1, about on this function. So the lemma says that if you consider the function from the positive real numbers to the reals given by precisely that formula for every positive real number x, then when we compute the image is the closed interval for infinity. Second, you see when x is equal to 1, this takes the value 4, and what 2 says is that only at x equal to 1 is the minimum attained, so that at all x different from 1, we actually have greater than the minimum, which is 4, which is f of 1, right? Which is f of 1. Okay, so and third is that for every element of the image, we can predict the 2 points that hit it, right? The pre-image, as the roots of certain polynomial. Now, a certain specific polynomial that of course depends on this R. Right? Now, 1 and 2. I mean, this is quite easy because the limit when x tends to infinity is obviously infinity, and when x tends to 0 on the right is it is also infinity. So this is just look at the formula. Okay, so these two limits, right? I mean, so you have the positive real numbers, and then you know that this limit is infinity, and very far away is also infinity, right? So maybe I can draw it here. So when tending to 0 on the right is infinity, and then very far away is infinity. Okay, right, and but there's only one point where the derivative is 0. And namely, for x positive, it's only x equal to 1. So this automatically implies 1 and 2, right? I mean, just by the intermediate, by basic calculus. It's not the intermediate value theorem. It's the okay, by Rolle's theorem, let's say. And for 3, well, for 3, then we see that you see, if we are going to have x plus 2 plus 1 over x equal to r, then this is because x squared plus 2x plus 1 is equal to rx, and this is because x squared plus 2 minus r times x plus 1 is 0, right? Okay, so this is important. So okay, so this will be important. But so you see, the thing is, when r is in the image of this function, these are the two roots, right? So okay, all right. Now let's perform the analysis of tau of the Möbius transformation for the different types. So in the hyperbolic case, namely when it's multiplication by alpha, by positive real alpha, then just by, you see, by this lemma, we see that this is a real number greater than 4. Greater than 4 because alpha is not 1. Right? Alpha is not 1, so it's greater than 4. Okay. In the elliptic case, one computes, and then it turns out that since it's alpha in the circle, here maybe I should say here also different from 1. 1 over alpha is alpha conjugate. So I obtain, so this one is 2 plus 2 times the real part of alpha. But the real, but since we are in the circle, right? Since alpha is in the circle, its real part, it's between -1 and 1. And so 2 times 2 times that is between -2 and 2. But when I add 2, it's between 0 and 4, open. Okay, open. Maybe here when alpha is -1. All right, so here I should write closed. When alpha is -1. Okay. Right, because if alpha is -1, its real part is -1. Okay. Fine. And then in the loxodromic case, I compute, right? So you get the same. And now I claim that I land here. Right? So now the thing is, I cannot land here. I cannot land there because if I landed there, then I would be in. Then I could apply 3. I could apply 3 and see that the roots of this the pre-image under this function with domain R positive are the roots of this. But then I would have, you see, a root that does not live on the domain. So I would have at least 3 roots of a polynomial of degree 2, right? So I can argue that at least this number is not in R greater than 4. And I leave it to you to complete the argument to see that one lands, that one actually lands outside all the positive real numbers. Okay, so we have computed, tau of the standard examples. In these standard examples, we see that we fall in 4 sets that coincidence are pairwise disjoint, right? So they are pairwise disjoint. So this means that I mean these are obviously pairwise disjoint, right? So the four places where tau lands. So this tells me that if I take two different types, they fall in different in disjoint sets. So this means that not only parabolic implies 4, hyperbolic implies greater than 4, elliptic implies between 0 and 4, and loxodromic implies everywhere else, but in every place I have also the converse, right? And since we did things in such a way that the tau of a matrix is equal to tau of any conjugate of the matrix, we see that what we have proved is this theorem, which tells me that tau is a complete invariant. That for a Möbius transformation, I know that it is parabolic if and only if when I compute this gives me 4. It's hyperbolic if and only if when I compute it gives me something in the interval, in the open interval for infinity. That it's elliptic if and only if, and here I should write a closed interval, and loxodromic if and only if I fall outside any of this. The picture, what is the picture? So this is the picture of the values of tau, right? So if I compute tau of nu and I land here, when I land here I have a hyperbolic, when I land here I have parabolic, when I land here I get elliptic, and everywhere else I have loxodromic. Right? So this something something a bit unfortunate about this is that somehow if I happen to have some floating point problem, it may be the case that when I program something, that instead of giving me the correct, let's say, hyperbolic, it gives me loxodromic because of some floating point problem. But anyway, now the other picture, the other nice picture is for those Möbius transformation with exactly 2 points. I compute not only I can compute not only the trace but the multiplier, right? In the parabolic case doesn't enter here, right? Because somehow the parabolic case is even is kind of one decides whether it's parabolic or not before even asking about multipliers. And so the correspondence is that if the multiplier is of certain color, then the trace is of that same color, right? So if the multiplier lands here, then the Möbius trace lands here. If the multiplier is here or the multipliers are here, then when I compute the trace, I'm going to get this, and the same for the complement. Okay, and actually, kind of the relation between this and this is that the passage from here to here is given precisely by z goes to z plus 2 plus 1 over z, as we saw before. Okay, so that's the trace, with which then you see the moral of the story is that it is something very easy to compute if you give me the matrix, right? And one arrives at the formula. Another moral is that one arrives at the formula by making some simple considerations, and by making some simple considerations, and keeping in mind that one already has a function invariant under conjugation, namely the trace, the usual trace of a matrix, right? And that is how one arrives at this formula. Okay, so far so good. And now let us speak a little bit about PSL2C and PSL2R. So I'm going to be seeing two different aspects. The analysis is not going to be terribly deep. But it's going to be two different aspects seemingly unrelated. The first one is that while you see we already saw that PSL2C and the PGL2C, they are both isomorphic to the group to the Möbius group, mob plus of C bar. We saw that. Okay, which can be said in a slightly different way by saying that the inclusion of the special linear group in the general linear group induces the isomorphism. Okay, and then the point I want to make is that when one asks whether the same happens for the real numbers, that is whether in the real case one also has isomorphism, it does not happen. So that's the first thing. So that in the real case, while the inclusion of the special linear real group in the general linear real group, while it does induce a homomorphism, like obviously, and while this homomorphism is injective, something that can be shown very easily, it is not surjective, right? And it's very easy to give things that are not in the image. The idea is pretty much that to take anything with the negative determinant, because when you have something with negative determinant, when you want to represent the Möbius transformation with something of determinant 1, you have to divide by the square root of the determinant, and then that takes you out of real numbers. That's kind of the basic idea of the basic reason why it's not surjective. So here you can see something of negative determinant, and you can check that it's not in the image. And the exercise is to compute the index, right? I mean, so this one occurs naturally as a subgroup of this one, so compute the index. Somehow the fact that this is not surjective, and somehow, when you compute the index, that somehow allows you to that's something that later on allows to interpret certain elements here as isometries that reverse the orientation of the hyperbolic plane. But okay, but that will be in the future. So okay, so that's one aspect, right? One aspect that I wanted to see, that is that when one goes from the complex to the real case, this the fact that these are isomorphic does not, the analog does not hold in the real case. Okay, and then the second aspect is that I want to characterize the complex matrices of determinant 1 that actually belong to that actually have real entries. I want to characterize them in terms of their action in C bar, right? I mean, so somehow take an invertible matrix, a 2x2 invertible matrix with complex entries. Then I ask, okay, are their entries all real or not? Right? And then I want to characterize the answer in terms of the geometry of the action via Möbius transformations. And that's what the next theorem says. So for that, I need to define already the upper half plane. So this is going to be one of the main objects of the course. So the complex numbers with positive imaginary part, right? Very easy to draw. So if that horizontal line, you are seeing the upper half plane, so quite easy to draw. And the characterization for such a matrix is given as follows. So it is equivalent for a matrix, for an invertible matrix with complex entries and determinant 1. So determinant 1, so I'm already assuming determinant 1. It's equivalent that the associated Möbius transformation preserves bijectively the upper half plane, that it preserves bijectively the closure of the upper half plane, which then would be, U bar is the topological closure, and then it's equal to U union R bar, where R bar is the topological closure of R in C bar, and then you can see that it's R union infinity, right? This is very easy. Okay, preserving this bijectively is equivalent to, just preserving this, sending this into itself, and sending R bar into itself. Just only preserving them is enough for knowing, for instance, that this is preserved bijectively, and this as well, and hence also this, right? And all of these conditions are equivalent to the matrix having actually real entries. Okay, so the proofs are not, the proof of this equivalence is not very hard, and relies a lot on the continuity of mu a, right? So on knowing that mu a is actually a homeomorphism. So let us do the proof. So the proof I'm going to do it 4 implies 3 implies 2 implies 1 implies 4. So kind of all the other way around. So let's start with 4 implies 3. So if it actually has real entries, then of course we know this, and of course we know actually not only this, but let's say by continuity this, right? Or by plugging directly infinity. Right? Okay, so to show that this happens by continuity, it suffices to show that at least one point here goes inside here, right? Just by continuity. Why? Because R bar, the complement of R bar in C bar has two connected components, one of which is U. So if one point in U lands there, then the whole connected component lands there. Okay, yeah, this is just by continuity. Okay, now the point. Well, I take a special point, which is the complex number I. But now for the complex number I, let's say that I write A equal to the alpha, beta, gamma, delta. So that when I compute mu A of I get this, and then the standard trick, in order to be able to perform this division, then I multiply by the conjugate of this guy. Right. So and here I should have written. It's not. Sorry. It's not this. It's the conjugate of this guy. So it's delta minus gamma I. And the imaginary part. So you see. So you see it's alpha delta minus gamma beta. divided by this. So the imaginary part is this, and since we are assuming determinant 1, this is 1, so the imaginary part is positive, and we are done. Okay, so that proves 4 implies 3. Let's go to 3 implies 2. So suppose this containment and this containment, and then notice, so you see this one is a circle in C bar because R bar is a circle in C bar. So what this tells me is a circle in C bar contained in another circle in C bar. Think about it, and the only way that can happen is that that this circle is actually the whole thing. So this means that we actually have equality, and then the other equality, this equality, then follows just because this is a homeomorphism. Okay, and because we know this, right? So since we know this, then from the other connected component of C bar minus R bar, from the other connected component different from you cannot land here. Right? So then you must have equality, and you cannot land there. Just you see because it's a homeomorphism. Right? Okay. Right. So this proves 3 implies 2. Let's go to 2 implies 1. So we suppose this, and we want to show this. But see, you see, mu a of u is the interior of u bar. Obvious, right? And mu a is a homeomorphism. So taking interior before or after gives you the same. By hypothesis, this one is u bar, so you have the interior of u bar, which is u itself. So 2 implies 1, and 1 implies 4. That's a bit tricky. So suppose this, right? So suppose 1. Then you compute, right? So mu a of R bar is the complement in u bar of u. So okay, complement in the closure. Because mu a is homeomorphism, you can separate. Separate this. Now mu a of u is by hypothesis this, and so you get mu a of u bar. But mu a is continuous, so mu a of the closure of a subset is contained in mu a of this, right, by continuity. So here you can pull out the closure, but this closure mu a of u is again by hypothesis this, so it gives you this. So in the end, you know, this game tells you that mu a of R bar is contained in R bar. With a little bit more work, you can actually just show that there's equality, but this containment, this contained in this suffices for me. Okay, so now we want to show that A has real entries, right? Because we already assumed that it has determinant 1, and we are assuming that it has complex entries. We are assuming this, and we want to show that A has actually real entries. Okay, so one way to show that a number is real is to show that it's equal to its conjugate, to its complex conjugate. So that's what we do. We take the complex conjugate of A, and the point is that a very easy computation shows you that for Z in R bar, you have this. I mean, here you need mu b of Z to be real, to be finite. yeah, so that you can actually take complex numbers. I mean, you just be careful with that. There's no problem, right? Because at most one value of z, this is infinity, so you have plenty of real numbers, plenty of z's for in R bar for which this is real and not infinity. Okay, so this is a simple computation, right? Just playing with alpha z plus beta divided by gamma z plus delta all conjugate. So you arrive at this. But you see, mu a of R bar is contained in R bar. So this means that here you have equality. When you conjugate, you get the same. Okay, so this means that for infinitely many points, z, we have this the equality between this and this. So the Möbius transformations of B and A have to coincide, right? Because they coincide in at least 3 points. Okay, so they are the same. But then, since both of them have determinant 1, right? So it's obvious that that B has determinant 1. So since both of them have determinant 1 and both of them that represent the same Möbius transformation, they are either equal as matrices or one is minus the other. Right? So if A is equal to B, I'm done, right? Because then alpha is equal to its conjugate, beta is equal to its conjugate, etc., which is what I want to show. So let us assume that it's not the case and arrive at a contradiction. Okay, so if this happens, then what happens? Then you see alpha is equal to minus alpha conjugate, right? I mean, from this we obtain this, right? Which is another way of saying that alpha plus alpha conjugate is 0. And this means that the real part of alpha is 0. And I can apply that to all the 4 entries, alpha, beta, gamma, and delta, and I arrive at this, that all the real parts of all of them are 0. So we can write them as real multiples of I. Okay, but then in that case, I do that, right? And then I write alpha equal to AI, beta equal to BI, etc. And now I again go back and evaluate at I, right? When I evaluate at I, you see, there's a cancellation here because there's I everywhere. Okay, I cancel, and I arrive at this, which again I multiply with the complex with the conjugate of this one, so that I obtain this, and I can compute the imaginary part. But you see, the imaginary part is AD minus CB, and I am assuming this, so this means that this one has positive imaginary part. So the imaginary part of this, which is AD minus BC, is positive. Okay, but then I compute the determinant of 1, the determinant of A, which I know is equal to 1 on the one hand, and on the other hand, because of these equalities, I have this. The determinant is multilinear, right? So I can pull this I, and then also this I, and then I get a minus. Determinant of this guy, but the determinant of this guy is positive, so minus that is negative, and there I have my contradiction. Right? Okay, so what must happen? That this is impossible, so this must be the case, but if that's the case, then it's because it has real entries. Okay, so that's it. Summary of the class. First, we saw in the trace that we found a function on GL2C that is invariant under rescaling rescaling any matrix by a non-zero complex number. It's invariant under conjugation, and then these two things tell us that whenever if I have two matrices that give me the same Möbius transformation, then the value of tau, the value of the function is the same, and also the value of any Möbius transformation is equal to the value at the associated standard example, and also the function was defined in terms of the trace of matrices, because we already knew that the trace of matrices is invariant under conjugation of matrices. And then with these things, and then by computing what happens in the standard examples, we arrived at a perfect invariant in a way, in the sense that if you give me a matrix, if you give me a matrix in GL2C, then just by computing alpha plus delta square divided by the determinant, I know automatically if the Möbius transformation associated to the matrix is parabolic, hyperbolic, elliptic, or loxodromic, just by looking at the value, which should be 4, real number greater than 4, a number in the closed open interval 0, 4, or in the rest of the complex plane. So we found a function that does the job of deciding the type of a Möbius transformation for us in a very easy, straightforward fashion. Second, we studied a bit of PSL2C and PSL2R. The first thing we saw is that PSL2R is not isomorphic to PGL2R, although it's included, in contrast to what happens when we take a PSL2C and PGL2C. And second, for a complex matrix with determinant 1, we characterized when it has real entries in terms of its geometry, right? I mean, in terms of its action on C bar as a Möbius transformation. Okay, so in the next class, I think I'm going then to say a little bit about a picture of SL2R. Okay, but that's all